Okay, so this video is on section 1.3, evaluating limits analytically. I'm going to take you through the properties of limits as well as the first two examples in this lesson. So in section 1.2, you learned that the limit of a function as x approaches a real number c does not depend on the value of the function at x equals to c. And there were three different cases where I drew you a picture of where the limit of the function as x approaches c is equal to L, which just means where the limit exists. So there was the first case, so this one right here, where the function value at x equals to c matches the limit. Okay, and that in that case, that's when the function's continuous. And then there's the case of where the function value is something other than what the limit is. So the function is approaching or seems to be approaching one value, so seems to be approaching L as x approaches c from the left and the right hand side. However, f of c is something else. It's not what we would want the function value to be. And an example of a type of function where this could happen is like a piecewise function, where it's, say, defined, the piecewise is defined everywhere, maybe except for at one x value, and at a certain x value, it's equal to something completely different. And then the third case of whenever the limit exists, but the function might not be defined there at x equals to c. So that example would be like if there's a hole in the graph. So where the function isn't actually defined at x equals to c, that's okay though. The limit as x approaches c can still exist if directly to the left of x equals c and directly to the right is still defined, and the function seems to be approaching a value L. Now, there are times, nice times, when you can evaluate the limit of a function by direct substitution. And all that means is that you're evaluating the limit by plugging c in to the function. Just plug in the value in. And this works for case one. So this first picture. So this is really whenever the function is said to be continuous at c, which we're going to talk more in depth about continuity in section 1.4. We're going to go deeper and talk about continuity in a more formal way using limits. But for functions that are continuous, we can use just direct substitution to evaluate the limit. And that's nice, but it's not always true. So what we're going to talk about next, which is going to be kind of a stepping stone for us with evaluating limits analytically, is we're going to talk about different properties of limits. So basically, it's if you're taking the limit of a function that you could think of as being like a sum or difference of two functions, or a function times another function, or a function divided by another function, right? We've talked about these functions that are created from applying operations like addition, subtraction, multiplication, division, where you're given a function and you think of it in that way, or composed functions, right? A function inside of another function. And for evaluating functions like this, we have these properties of limits, which in your textbook, I believe, has the proofs for all of these properties. But we're just going to talk about using them. So if you have a function that you can think of as being created from adding or subtracting functions, so like a common function like we'd think of like this would be polynomial function with multiple terms. So if you have a function that you can think of as adding or subtracting other functions, you can think about evaluating the limit of each part of the sum or the difference. So if you're taking the limit of f of x plus g of x as x approaches c, you could take the limit of f of x as x approaches c plus the limit of g of x as x approaches c. If you have a function that you can think of as a function times a constant, that's the scalar multiple property for property of limits. So for example, if you were taking the limit of 3x squared, you could think about pulling the 3 out and then evaluating x squared for whatever x is approaching. And then the multiplication property of limits is if you have a function that you can think of as a product of two functions, you can take the limit as x approaches c of each factor. Division, you can take the limit of the numerator and the denominator separately, and this works as long as the limit of the denominator is not equal to 0. When you have a function that you can think of as a power, you can actually just think about taking the limit of the function that's inside that power and then raising the limit to that power. And then composition, this one's the tricky one, but it should make sense. So if you have a composed function, so f is the outside function, right? F is the outside function, and then g as the inside function. Now, when you have a composed function, so inside function, outside function, and you're evaluating that function, you think about evaluating from the inside out. So like you would be thinking about evaluating g. Well, when we're taking the limit, you think about taking the limit of the inside function. So let's say that the limit of g of x as x approaches c is L. And then we can think about taking the limit of f of x as x approaches L. Okay, so you figure out what the limit of the inside function would be as x approaches c, and then take the limit of the outside as x approaches whatever that limit of the inside function was. I think it'll make more sense as we go through some examples. So note, in general, the limit can be taken of each piece of an expression. Then the results of those limits may be combined using the algebraic rules of the expression, right? So when we're adding or subtracting, we took the limit of each piece and basically added or subtracted the limits. Multiplication, you take the limit of each factor and then multiply those limits together. So let's look at some actual examples. So you might have a problem like this. We're going through these first two examples mainly to become familiar with what these properties are. I'm going to write out all the steps of applying these properties, but once you're familiar with them, you do not necessarily need to write them all out. Okay, so if we wanted to take the limit as x approaches 3 of this function in here, so 2 times f of x minus 4 times g of x, okay, well, what stands out to me first is I have a difference of two functions. So I could think about taking the limit. Actually, let me change this a little bit. So we could think about taking the limit as x approaches 3 of 2 times f of x minus the limit as x approaches 3 of 4 times g of x. And the only reason this is working is because we are given information about the limit of f of x, limit of g of x, limit of h of x as x approaches 3. If x was approaching a different value, like this is a pretty contrived example, so that we have enough information to evaluate the limit. Okay, so then what I notice from here is that f of x is being multiplied by 2, g of x is being multiplied by 4. So we can use that scalar multiple property and we can pull the 2 out of the first limit. And pull the 4 out of the second limit. I didn't really need those extra parentheses. Okay, and then I know that the limit of f of x as x approaches 3 is 8. So I can replace that limit with 8 minus 4 times, and I'm given the limit of g of x as x approaches 3 is negative 2. So then it's just simplifying that. So is that 16 plus 8 would be 24? So that limit is equal to 24. Okay, so what stands out to me in this next example is this exponent. So we have 2 times g of x being raised to the second power. So if we wanted to use the power property, right, so number 5 here, for limits, we could think about pulling that exponent of 2 outside the limit. And you know what? I'm noticing the 2 inside here. We could also think about pulling the 2 outside of this limit. So 2 times the limit as x approaches 3 of g of x, all squared. And then we know that limit of g of x as x approaches 3 is -2. So this becomes 2 times -2 squared. So that's -4 squared, which is +16. Ooh, this one looks pretty complicated. Okay, so let's see. First, I'm going to just go with what sticks out to me. So what I see is I have a sum of 2 functions, right? First function, second function. So I'm going to take the limit as x approaches 3 of this first function, which is the cube root of f of x over g of x, plus the limit as x approaches 3 of 4 times h of x divided by x plus 7. Okay. So each of these limits now have fractions where we could think about taking the limit of the numerator and denominator of each of those fractions. So the limit as x approaches 3, make sure you are using proper notation, of cube root of f of x, you have to have x approaching 3 every time you write the limit, over the limit as x approaches 3 of g of x, plus, in the numerator, I'm going to pull out the 4 and take times the limit as x approaches 3 of h of x, over the limit as x approaches 3 of x plus 7. Okay, now cube root is the same as the 1/3 power, right? So I could use power rule or power property for limits. And I could think about taking the cube root, or I could change that to the 1/3 power. So the limit as x approaches 3 of f of x, all raised to the 1/3 power. That's the same thing as cube root. You could write either. And then I know what the limit as x approaches 3 of g of x is. Isn't that -2? Or we could do the here, I'll just do the substituting all in one step. So I'll leave this as the limit as x approaches 3 of g of x plus 4 times the limit as x approaches 3 of h of x. And then we're going to end up wanting to use direct substitution for this bottom limit. Oops. But I'll just still write the limit here. You don't have to. You don't have to write out all of these steps if it's pretty obvious to you. Okay, so replacing the limit of f of x as x approaches 3 with, is that 8? 8. So that's 8 to the 1/3 power, or the cube root of 8. And then the limit of g of x as x approaches 3 was -2. the limit of h of x as x approaches 3 was 0. Okay, so that's not very interesting. And then using direct substitution for this denominator here. So just plugging in 3 for x. 8 to the 1/3 power is 2, right? Cube root of 8 is 2. So 2 divided by -2 will just be -1. Okay, so that's the first example, just some practice of using, you were given some limits and then thinking about taking the limit of functions that were created from applying operations to other functions. Same type of problems in this second example, but to figure out to figure out the limit values, we're going to read these graphs. So we have the graph of f and the graph of g. To find the limit as x approaches 0 of this first function, I see I have a sum of two functions. So I'm going to first think about taking the limit as x approaches 0 of 2 times f of x squared plus, and then it'll be the limit as x approaches 0 of 3 times g of x, or I can pull that 3 out. And then I want to get it to the point here where it's the limit of f of x by itself. I know we can pull the 2 out. So we would have equals 2 times, I'm going to do this in 2 steps just so everyone can see it. So the limit of 2 times, and then it's f of x is squared, plus 3 times the limit as x approaches 0 of g of x. And then we can use the power rule for a limit, so it'll be 2 times the limit as x approaches 0 of f of x squared. Okay, so the limit as x approaches 0, right? So as x approaches 0 from the left and the right appears to be 2. And that's squared. And then the limit of g of x as x approaches 0 looks to be 0. So that ends up being 8. 2 times 2 squared is 8. Okay, I'm going to shrink this down to do the next limit. Should have probably given myself a little bit more room here. Okay, so what stands out to me in this next one is this division bar here. So I'm going to think about taking the limit as x approaches 3 of the numerator divided by the limit as x approaches 3 of the denominator. And then the function that we're taking the limit of in the numerator is a product of two functions. So we can think about taking the limit of each factor in the numerator. So limit as x approaches 3 of x squared times the limit as x approaches 3 of g of x. And then divided by the limit as x approaches 3 of f of x. And we can use direct substitution for the limit of x squared as x approaches 3. That'll just be 3 squared. And then the limit of g of x as x approaches 3. So I go over to the graph of g, and we're looking as x approaches 3 from the left and the right. It seems like the function is approaching 1. And then the limit of f of x as x approaches 3 looks like the function is approaching -1. So that simplifies to be -9. I'm going to move this. I'm going to resize it. Just move it up a bit. Okay. So now the limit of a composed function. Okay, so we first want to think about taking the limit of the inside function, because this is going to end up being equal to the limit as x approaches whatever the limit of f of x as x approaches -3 is. Right, that's going to end up being what the limit of g of x is as x approaches whatever the limit of f of x is as x approaches -3. So I go to the graph of f of x, and as x approaches -3, it looks like the function is approaching -1. And then the limit of g of x as x approaches -1 seems to be +1. So even though the function value at -1 for the function g is +2, it looks like the function is approaching +1. So we say the limit would be +1. Okay, so for D, we can actually treat this like a composed function as well. So this would be the limit as x approaches whatever the limit of the inside function as x approaches -1 is. Well, to evaluate the limit of x squared as x approaches -1, we can just think about substituting -1 into x squared, and we would get +1. And then the limit as x approaches 1 of the outside function g of x looks to be -1. Okay, we have a one-sided limit next. So what stands out to me first is the division bar. So I can think of this as the limit as x approaches -1 from the left of 2 times f of x, and I can pull that 2 out. And then divided by, that'll be the limit as x approaches -1 from the left of g of x squared, and I can actually use the power property of limits, and I can pull out that exponent of 2. So reminding myself, this is a one-side limit. So 2 times the limit of f of x as x approaches -1 from the left is +1. And then the one-sided limit as x approaches -1 from the left of g of x is also +1. So this ends up simplifying to be +2. Okay, this looks like a tricky one. What's standing out to me first is I have 5 minus this function. So using that sum property for limits, or sorry, the sum difference property, which we're using the difference. So the limit of 5 as x approaches -1, which the limit of a constant is just going to be the constant. It'll be 5. Minus the limit as x approaches negative 1 of the square root of x squared times the quantity 3 plus f of x. Now, square root is the same thing as the 1/2 power. So I could actually think about applying the power property for limits. And you can either rewrite that as a square root or as the 1/2 power. I'm going to write it as the 1/2 power. So like I said, limit of the constant is just the constant. So that's 5 minus, and then we have a product of two functions. So that's the limit as x approaches negative 1 of x squared times the limit as x approaches negative 1 of 3 plus f of x. Well, this is a sum. So using direct substitution to evaluate the limit as x squared as x approaches negative 1, I can just use direct substitution. That's just going to end up being 1. And then times, I can split that limit up. So the limit as x approaches negative 1 of 3, that's just going to be 3 plus the limit as x approaches negative 1 of f of x. So what I really need to know is what's the limit of f of x as x approaches negative 1. From the left, it looks like f of x is approaching 1. And from the right, it looks like f of x is approaching 2. That means, since the one-sided limits are approaching different values, the limit is d and e. It does not exist. Oh boy, what does that mean? Well, if we have that part that doesn't exist, so right now, here's what we have. That just ends up being 1. So that ends up being 3 plus d and e. That means that this limit is just d and e. Doesn't exist. I'm going to say therefore d and e. Now, what if this were a one-sided limit? Let's change colors. What if this was x approaching negative 1 from the left? Or to make it, or from the right, because we haven't done any from the right. So if this were x approaching negative 1 from the right, where if I put this in here, it doesn't matter there, but from the right, if I go back up to f of x, that would be 2. The one-sided limit exists. So that would end up making this 2. So this would end up simplifying to be 5 minus the square root of 5, or 5 to the 1/2. So in that case, that would be the limit. The limit would exist if it were a one-sided limit, but the two-sided limit here doesn't exist because you get that one part that's d and e. Okay, so these were 2 examples of you're given information about some functions, and then you thought about taking the limit of functions that were created from those functions, applying different operations to create those new functions. And we'll continue on with section 1.3 in class.